Okay, hello everyone. As Radim just said, yeah, my name is Piotr, and I happen to work in his group in Olomouc. And today I'm gonna tell you about some recent progress that I've been part of in the aiming at the aiming at the optimal control of quantum motion in many different systems. So the starting point for the any trapped quantum system would be the linear approximation, would be the quantum harmonic oscillator. And in this linear arts regime, we are allowed to do some operations such as squeezing, displacement, and rotation. And these operations are preserve Gaussianity of the states. So with this we are not able to unlock the full potential that comes with the non-Gaussianity of the states. And there are like two standard ways of how to escape from this Gaussian prism. The first one is to couple your harmonic oscillator to some two-level system, or in general some nonlinear system. And there are like many systems in which we can do it, such as trapped ions, some mechanical oscillators, and many others. The other approach is not to couple to anything, but rather use the intrinsic nonlinearity of the potential of the confining potential itself. So to go beyond this harmonic oscillator approximation. And this kind of thing would be natural for stuff, for example, for the stuff that is levitated like single atoms in optical tweezers or levitated nanospheres and many other systems. So in this talk, I'm going to address both of these approaches. But let me start with this intrinsic in this non-harmonic potential thing. So, like if you trap something, you usually do it by some kind of electromagnetic field that has some characteristic length scale. So it can be like a tweezer, waves of the tweezer, or like some trap period in the optical lattice. And this characteristic length scale is around usually like 100,000 nanometers. And then depending on what you would like to trap, either it can be like something small like an atom, or something big like some solid state piece. So it's a sample like a nanosphere. Your motional ground state has different properties because the extent of this wave function depends on the mass. So for atoms, the size of the 0-point motion is or the order of the potential, while for these like very massive systems, it's much smaller. It's of the order of the let's say picometers and smaller. So in order to somehow to say something about the type of the quantum dynamics that we have access to in this kind of systems, we introduce a so-called non-harmonicity parameter that is just the ratio between the size of the wave function to the size of the potential. And depending on this eta parameter, we have different types of the quantum dynamics in the system. So in here, just to decrease the eta, we make the potential larger. And as you can see, if the eta is very small, then the non-Gaussian properties of the states appear during the later times. And this provides, well, a problem. If your system is like very weakly non-harmonic, it's very hard to produce these non-Gaussian states. So, so for nanoparticles, this is extremely small. So here I'm going to address like both of this regime, large eta, small eta. And let me start with a specific task and a specific system of the levitated nanoparticles. So what's a levitated nanoparticle? It's actually a piece of glass. It's like a sphere that has been proposed to use in the experiments that probe both quantum mechanics and gravity due to its large mass, well, relatively large mass. And it can be manipulated by a variety of potentials like optical tweezer, electrostatic, or magnetic potentials. So the aim is to have a control over its center of mass motion such that we can delocalize it and see some like non-Gaussian features, some quantum features of its state, well, to probe the gravity and quantum mechanics at the same time. But the problem with this setup that it's extreme decoherence prone. The usual coherence times are like much larger than what we beyond what we expect to see when we see beyond when we would expect to see some quantum features just coming from this small eta. So we came up with the protocol in which we use this hybrid potential. So the idea is that we have the nanoparticle trapped in a tweezer. This is like really tight potential. And then we have underlying very shallow and wide potential that can be non-optical, like electrostatic. And then the idea is to as follows. So here is the phase space picture with the phase space trajectory. This is position momentum. We release the tweezers, and then this nanoparticle starts to evolve in this part of the potential that happens to be like inverted harmonic potential. It expands, it hits the quartic wall, it self-interferes, and then it comes back in here, and it can be recaptured by the tweezer and measured. So this protocol has been we presented this in this paper. We made like a full analysis of the coherence, timescales, and so on. But the problematic thing from the theory point of view was how to describe this large phase space expansion in the quantum regime. And we did like two different ways. This is like purely numerical approach. This is like analytical approach. And then we went step further and we analyzed how to optimize this potential shape to provide the best dynamics. And if you would like to know more about the experimental progress, you can go and see Nadine's talk on Friday. All right, but what about the regime of atoms? So like this eta being large. So imagine that you have a single atom in a tweezer, and what can you do? You can move it around, and you can like change the depth of it. This is like a natural possibility what you can do with the tweezer, and whether like the question is like what can you do with it? So can you get the full control? So you can imagine. So in this scenario, I just move the tweezer around like in some specific motion, and I am able to transfer the ground state to the Fock state. But the question is, what kind of motion, what kind of movement of this tweezer you need to have? The answer is like in the so-called quantum optimal control. So we expand this displacement of the tweezer in some Fourier basis with some weights, and these weights are varied, optimized with respect to some cost function. So for the state preparation, this is just the overlap with some target state, which in that case was the Fock state, with some time evolved state coming from this dynamics with the shaking. And we found out that this approach is very versatile, meaning that we do not we can not only prepare Fock state, but like really variety of states, like these GKP states. Here is the motion of the tweezer that produces this kind of state. And we went beyond, so we can implement unitaries, we can do measurements, cooling, state stabilization, many other things, and you can find it in this preprint. So the question is whether we can marry two words, whether you can use the shaking for nanoparticles. And the answer is yes, but first you need to play some trick. So the trick is first you need to squeeze. So this is just the cubic potential with the linear control. So first you expand, then you shake, and in the end you compress it back so that you can generate, more or less any state. All right, so that was like the side of this potential modulation, yeah? So, but the question is whether we can do similar full universal control with the spin oscillator coupling. And the answer, yes, it has been checked that like you can, with the optimal control, you can generate more or less any state that you would like to have. So we asked the question whether we can optimize for some specific tasks. So in the both yesterday and the day before, we heard about like some stuff about the quantum metrology and some specific tasks. So we are interested in the force sensing. So it's kind of known that if you'd like to measure some displacement in the phase space, you can squeeze your state so that you improve the accuracy because you have these like very fine phase space features that enable you to distinguish the state better. So, but the problem is when you don't know in which direction your force acts. So it can either you can vary from shot to shot in experiment, or your state can rotate in the phase space. And people found out, what's the solution? Yeah, you need to prepare a state that has these small features in every direction in the phase space. So you can take a Fock state, and if you displace it, if you randomize the direction in which you displace, they provide the quantum enhancement in sensing. But we ask a question what kind of states are the optimal in the realistic setting? So we took this spin oscillator system. So this we have some decoherence, some of the motion in here. We have James-Cummins couplings, and we have the optimal control done via the driving the qubit only. And for the measurement, we took just the excitation resolving measurement. So we assume that at the end of the state preparation and sensing stage, we have the access to the Fock state occupation, and we take just the Fisher information with respect to this measurement. And what we find out is that depending on the decoherence and force amplitude, not only Fock states are not optimal in all of the cases, as one would to some extent expect, and apparently these amplitude squeezed cut states are optimal depending on the in some regimes. So we have found out some kind of like a meteorological phase transition to some extent. And if you like to know more about the system in which this kind of thing can be realized, like go see Mateo's talk later today. And and this is the preprint in which we have these results on the optimization of the spin oscillator for the force sensing. And so just to give you some take-home message, in general, there are like many different ways how to control quantum motion. And if you use some tricks like squeezing, like a quantum optimal control, you can basically do whatever you want. And well, if you are interested in any kind of any type of these schemes, you can just reach out and we can discuss. So my final slide is just the people that were involved in these projects. That's it. Thank you.
Thank you. We have space for questions. Davide.
So just referring to the last part of where you consider this the improvement by the squeezed amplitude cat. Do you ever tried, or there is a reason why, for example, if one uses compass states where you have superposition of more coherent states, could be more useful for phase detection?
So for the phase detection, we haven't checked the phase detection. Only the results will be different for the if you would like to measure the phase, And I can imagine the compass states due to the fact that they have the orientation of these small fringes are like kind of aligned to the change of the phase, So probably it will be something different, In here, it's just the fact that it's specific some kind of like process in which you pump your state somehow, like I don't know how to even call it. You can imagine, right? Like you pump it up.
All right. Another, Marcin.
So in this last part, your parameter is phase independent, yes? So like naturally, this would suggest that the states should also be like phase independent. It should be phase symmetric, and your state is not, yes? So would you get the same if you average your state over the phase?
Yes.
Okay.
Meaning that because we only measure the diagonal in the Fock basis, and the states that are diagonal in the Fock basis are like rotationally symmetric. So, if I just take the diagonal part, it's gonna get like symmetrized in the phase space, and it's just gonna be different, Like the reason that this one is optimal is because we have finite resources, So like we have like specific state preparation protocol. It's just like some kind of easier to prepare this state than like fully symmetrized one. Because at the level of the properties, it would be just the same.
All right. It looks like there are no more questions. Thank you, Piotr, once more.